Hi everyone, welcome back. So this is going to be homework 2, and in this video I'm going to be looking at part 1a. So we're going to be numerically demonstrating the central limit theorem. Now to start, the central limit theorem says that in many situations when independent random variables are summed up, their properly normalized sum tends toward a normal distribution. Now this happens even if the original variables themselves are not normally distributed. And then a normal distribution looks a little bit like this. The bell curve you see here, centered on the mean. And it shows the amount of data that's, or the amount, the area under the curve that is present in each standard deviation away from the mean. So what we want to end up with is something like this. Now the way I'm going to show this is I'm going to make an array. Stop it on time real quick. I'm going to make an array. And so we're going to have a certain number of samples, and each sample is going to be represented by a row in that array. And each sample is going to have a specific number of data points. And when we average all those data points up, that is going to turn it into a one-dimensional array, and those, it should, according to the central limit theorem, normalize our data. So I'm going to start by importing numpy. And I want to specify the dimensions for our array. So number of samples. We'll go with 100. And the number of terms averaged in each sample. So an average. We'll also call it 100. Shift enter. Now what we want to do is we want to generate this data. We're going to make it random, and NumPy can actually do this random data generation. So np.random. We're going to specify that we want this random data to be from uniform distribution, because again, although we could generate it as normal distribution, we want to show that this happens even if the original variables are not normally distributed. So uniform, we want our data to be from -10 to 10, and we want to specify a size for our random data. And this is going to be what we specified above. So n samples, n average. And we're going to need this. Name it correctly. Unifrom. That is not the right word. Okay, so here's our data. Now what I want to do is I'm going to display it using a histogram. So again, NumPy has a nice histogram function. Histogram. And it's going to take in our data. So the data we want to display. So I'm going to call this samples. So samples. And then we're going to need the number of bins. So I'm going to make a variable for that. Call it n bins. N bins is not defined yet because we did not define it. And I will just say let's have 30 bins. Okay, so then it gives us our histogram here, and within this histogram, we have two arrays. Now this first array looks like it is the height of each bin, and the second array seems to be the location of the bin. So what I want to do is I want to put these into their own variables. So we'll call it heights and locations. So that pulled the first array into this heights variable, the second array into this locations variable. Now what I want to do is I'm going to graph it using Plotly. So from Plotly dot subplots import make subplots shift enter, shift enter, shift enter. And we're going to do figure equals make subplots and figure dot add bar. We're going to add bars because it's an histogram. X is going to equal the location. Y is going to equal the height. Okay, so here's our uniformly distributed data. You can see it goes from -10 to 10, and it's about normal. It's about uniformly distributed. Now, if we were to increase the size of our array, increase n samples, increase n average, n terms average per sample, we would have more of a flat line here. But this should work for what we're trying to do. So now what I'm going to do is I'm going to average the data in each row of our array, and that should, according to the central limit theorem, normalize our data. So it should look more like that bell curve from before. Now to do this, NumPy has a nice function again, np.mean samples. If we go ahead and run that, we get a singular number. That's because when we do the average of all the samples, it takes that entire array, two-dimensional array, it averages every number in that array. But we only want to average each row, so we can specify the axis that we want to do our averaging on. And here we go, we have a one-dimensional array. So I'm going to store this in, I'll just call it samples1. And then what I want to do, I want to basically copy all of this down and just redo the histogram. Redo the figure. Samples. We're going to change this to samples1 to use our normalized data. And everything else should work. So if we run this, we get something that looks, it's kind of normal. I think what will help us see this is if I add a lot more data. So I will go to 1,000 and we'll hit run all. As you can see, this goes to about a straight line for uniform data. And then what we have here, this looks a lot more like a bell curve, centered on 0. A lot more like what we're looking at right here. And you know what, I'm just going to go ahead and add another 0. It doesn't take too long to run. There, at this point, it's basically a straight line, and this really looks like it's a normal distribution. So we've basically seen how the central limit theorem is correct in that even if we have data that's not normally distributed, basically averaging it gives us a normal distribution. So that was part 1A of homework 2. Thanks for watching.